So next we're going to go to the land of engineering. So we've got Apostolos Tsoumelekas, who is a materials engineering manager for Skanska UK and the SCS joint venture. With over 15 years of experience in materials engineering, he specialises in concrete technology, soil engineering, and rock mechanics. Woo, indeed. While leading and providing technical support of innovative resource and carbon-saving initiatives. So welcome, Apostolos.
Good afternoon, everyone. I hope you're all refreshed and awake. We'll try to keep it that way, but I cannot guarantee it, yeah. So I'm Apostolos, materials engineer for Skanska. Today, I won't just look into this, the Excavation, Waste, London Clay Utilisation and Concrete Applications Innovation Project, which we'll call Ex-Clay, otherwise it will be here for a couple of days. But we'll go through the journey that we had since 2019 to where we are now. So before we go into the clay, a little bit about the London tunnels, which is what we are delivering. The SCS stands for Skanska Strabag joint venture. And we're delivering the tunnels from West Ruislip in London all the way down to Euston. So at the moment, we completed the Northfield Tunnel list, which is between Old Common and West Ruislip, and we're about to start the Euston tunnels. Now, I forgot to mention, these are about 46 kilometers in tunneling, about 9.5 meters diameter. So back in 2019, we were looking into what can we do with the clay that is coming out, with the tunnel arisings that are coming out from our operations. Now, we had estimated more than 5 million cubic meters of excavated material, 90% of which would be London clay. So we started looking into what can we do with that material that is coming out. Crossrail had Wallasey Island. We didn't have one of these, so we had to start looking into that. Now, outside of this presentation, one of them was a big change in our design. So in the West Ruislip area, we had an open cut where the trains are coming out of the tunnel and go further out. We changed that design, so there is the Coptel tunnel now, which is a cut and cover. So basically, we built the box and we covered it with the London clay that came out, and that's where we used about 1.2 million of those cubic meters. But we still had a lot to see what we can do about. So 2019, we were looking into circular economy principles. Can we reuse it back into the project? And that's when my equivalent in Arup, who is our designers, came up and said one day, why don't we use it in concrete? Back then, no one was thinking about using clay in concrete, especially waste. So we put together a consortium, and we called that team the Repurposed Excavated Rising Loop REAL. We like long titles, but we shortened them, yeah. So we started looking into exploring what can we do. Bear in mind, this is a year before we got the notice to proceed, so we were not even on site. And we got two options. One was calcining the clay and use it as cement replacement, and the other is expanded clay as a lightweight aggregate. So we explored both of those applications. We split the project in 3 stages, even though stage 1 is 1A and 1B. 1A was mainly to have a look and see if we can do anything with the clay that is coming out. 1B is to go into the lab and start looking into mineralogy, looking into concrete mix designs. And 2 was the aspiration of putting a pilot on site and start, as the clay comes out, we process it and we use it in the concrete that goes back into the tunnel. Now, what were all the benefits that we could have gotten from stage 2 rollout of REAL initiative? And we split them in. Of course, we got the waste disposal reduction. We're reusing the clay. We're not sending it for restoration of old quarries. Resource efficiency, circular economy. So we get something that comes out of construction going back in. Of course, we've got carbon benefits, because the purpose is to replace Portland cement and concrete that we were producing to use on the project, because we would use a lot of concrete and we still use a lot of concrete. Cost benefits, obviously. And then we've got the legacy part. So this is something, London clay, and we'll see as we go through, is a low reactivity clay considered in the cement industry, which means that no one is looking into those clays up until then. Well, no, now they started looking at them because of this. But back then, no one would look into the low reactivity clays as an option to use into concrete. Now, we started testing. One of the measures for reactivity of clays is the kaolinite content. So this is the highest the content, the higher reactivity of the clay. Now, normally, in the industry, we had kaolinite content of 90% as metakaolin being used in concrete, but no one has used something lower than that or had looked into this. Now, the results are from the London clay that we got from some trial pits from HS2 and Tideway. We got some samples from there. And we put them on the plot, and you can see that they're all on the lower bottom of this. At that time, it didn't seem too positive. But we moved on. Just to give you an idea of what the kaolinite content does, the more the kaolinite, you can see the strength going further up. I won't go into too much detail in that, but the stronger the clay, the stronger the kaolinite content in the clay, the higher reactivity. Therefore, you get higher strengths that you can use in structural applications. We did some lab trials just to see what is going on, and there you will see the LC3 reference. LC3 is something that the EPFL team in Switzerland have developed. It's the limestone calcined clay cement, the 3 Cs. And this is what we started looking at. You can actually get high strength development on low reactivity clays, which was surprising. Now, I mentioned that we looked into lightweight aggregate, and we did explore this, and we saw that we can use London clay as it comes out of the tunneling operations, a lightweight aggregate, but we chose to focus on the cement replacement because it has higher benefits for the entire industry. And of course, we had more applications than lightweight aggregate. Now, this is now stage 1B, where we go from feasibility review to actually in the lab, and we started testing different admixtures that go in the concrete, because of course we've got 120-year design life to look into, and we've got high durability requirements plus high logistical requirements for placing that concrete in a tunnel or in a shaft or everywhere that we've got inside of 2 kilometers pump lines and stuff like that. The problem we faced straight away, the industry doesn't have admixtures for calcined clays. So we had to start looking into developing admixtures specifically for our clay. And we started looking into whether we can add gypsum to help the clay, to give us more reactivity. We started looking into the mineralogy of the clays, how different they are from the 3 areas. We found that the clays that we tested are very similar, even though not identical, obviously, but they are similar. So that helped us, at least for the concrete perspective and cement perspective, to move on. Now, we moved into calcining some of the clay, which was easy because we're talking about 300 kilograms of clay at this stage. So it was easy to find a facility to calcine, and that's a different problem that will come up to the next slides. And this is how it looks like, yeah. I won't go. So we went in the lab and we started developing concrete mixes to see what we can get out of that material. Bear in mind, no one in the UK has used that in that scale back then. This is 2021 now. And we started looking into how it performs, see what the problems are, see what strength development we get, see workability, how fluid it is, if we can potentially pump it somewhere. And we started getting strength data. This was the interesting thing. So when we discussed it with our academic partners, they said there must be something wrong, but this is more than 20 batches that we did in the lab. So we were confident that there were not mistakes. We're getting high strengths of C40-50 for cement contents of 307. Don't ask me why we went with 307. Someone said that number and we said, let's go. A random number, but yeah. 50% calcined London clay, and we use 70% as well, which is outside of the codes. So with the Euro codes and design codes, you can go up to 55% replacement. We went to 70 just to see what happens. Now, we started learning from what we got from those trials. We developed more admixtures, new admixtures, just for what we want to do. And we started redesigning our concrete, optimizing our concrete mixes, making more specific to the project. We had applications in mind, but we were just trying to see if we can actually use it. Again, that's lots of months in there. That's November 2023 when we finished it. And these are the optimized, and we saw better strength development than previously. So as we gain more understanding of hands-on experience of calcined clay, we started understanding how it can perform and how it reacts with cement and the admixtures, of course. This is now 2 graphs that might not mean much to most, but it's incredible for me. The left-hand side is a mess. So this is the first phase where we couldn't get it to work more than 15, 30 minutes maximum. So bear in mind that from patching concrete to placing it, it might be an hour, 2 hours sometimes maximum. We couldn't use that. We would lose the trucks on the way in. So what we did with developing more LC3 specific admixtures, we saw that concrete is drying out gradually. So we can play with it more within the 2-hour constraints. Now this is a picture, just to give you an idea of how it looks. The samples are saturated, so they're a little bit, more vivid than what they normally are if they're dry. On the left-hand side, you've got 50% calcined clay, 50% Portland cement. Next to it is the 50% GGBS, which is the norm now for the industry. They start with about 50%. Then we've got the 70% GGBS, and in the end we've got, the 70% calcined London clay, and then the 70% slag GGBS. And now we go into Ex-Clay. Of course, we never got to the stage 2, where we have something that we can use on site, to go on a pilot on site, because lots of reasons. One of them is cost and program. But an opportunity came up with Innovate UK when they were doing a funding competition for decarbonizing concrete. And it was right when we finished REAL, when we sat down with Arup and our client HS2 and we said, okay, do we apply for it and see what happens, just to upscale what we have done for REAL. And luckily we were successful. So we got funding and we started last October. And now we're going to the stages of what we have done and where we are now. Unfortunately, the plan was that I come here and I show you the full structure, which was planned to be poured mid-September. We had a month delay because the batching plant is not ready yet. So it will happen at the end of October. But we'll go up to where we stand and what we are doing. Now, the scope was, as I said, built on the established R&D work, calcining London clay. And this is the big problem that we have. We started looking into facilities that could calcine the clay. Calcining is basically burning, and then grind it to a powder that you can use in concrete. Now we went out to the supply chain and we said, okay, we're planning to do this. Who can support it in the UK? There were 2 companies that came back that could do that to the scale that we want. But both of them had caveats. One of them was the clay needs to be less than 5% moisture content. Now we'll see some pictures. The clay that comes out of the tunnels with the deforming agents, the water that goes in, is about 40% moisture content. And when we started looking into who can dry it down to 5%, there was no one that could do that consistently, that we can put it in the kiln. Now the second problem was, after you calcine it, you have to find a facility to grind it. That was difficult as well, even though we could find some alternatives, but it was a problem. So to give you an idea, we ended up sending it to Tarmax CRH facility in Denmark, because it was the only facility that could take it, dry it, calcine it, grind it, and bring it back in the UK as a powder. Now, that destroys carbon footprints, and of course we're not saying that this is what we're going to do. We're going to take the clay and send it to Denmark, but this is a step to show to the UK cement industry that you can do it. The technology is there and we can do it. Produce concrete mixes, expanding on what we have. And we had, again, I'll go through the consortium, we had, again, admixture suppliers in, developing now admixture specific to the mineralogy of London clay, not just calcined clays. This is the big plan, that we want to cast the structure on HS2 using that clay. Bear in mind, this is a 120-year design life structure. We will test the concrete, obviously, structural, durability, performance. We've got sensors that we're going to put in, strain gauges, thermal monitoring, and everything that will go on for at least 6 to 10 years. Life cycle assessment, we will be doing that. We are in the process of completing it next week. And like I said, the carbon footprint of transportation to Denmark coming back destroys every other effort. And just to say on the carbon footprint, when you dry a clay from 40% to less than 5 to go in the kiln, that is the highest energy that you will use for carbon footprint wise. Now, since I'm here, I think I've got a little bit of time, I'll expand on that. So when we talk carbon footprint, Portland cement is about, let's say, roughly 800 kilograms per ton. So every ton of Portland cement that we produce, we have 800 kilograms of CO2 emitted. Now, 50% is from calcining limestone. Yeah, this is when you hit limestone, it will release CO2 because that's the chemical reaction. That's 50%. 50%, maybe 60%. Yeah, the remaining 50% is from the heat, the source of energy that you need to heat the kiln to the 1400 degrees. So people say, okay, it's because it's 1400 degrees. No, it's 40 to 50% is the temperature and the energy that we use there. The other is the CO2 that is emitted through the calcining of limestone. Now with clay, you've got 5% limestone minerals in there. So the CO2 that you will emit is minimal. And you need about 600 to 800 degrees, depending on the clay, for the heat. So without any, extended calculations, you can say, okay, we might save 70% from doing this. And this is the last bit that we will have on our report, which will be publicly open to everyone. About the detailed route to wider adoption and commercialization. So it's not about just HS2, it's about the next project. The next project that will have a vast volume of clay coming out, what can they do? And how will it can be included in the program and, of course, finance and commercial. Now, this is the Ex-Clay team. Lots of people involved. It's a massive consortium of people that we all have one goal, to see this going into concrete. So we've got academics, we've got Mineral Products Association is part of this, we've got industry representatives, supply chain, our designers, Arup, the client, everyone is on board to do this. And this is what really stands out for me for this project, collaboration. And when you've got an industry site that can do stuff as a demonstrator site. Now this is, you might have seen this picture earlier, or some of this. This is the clay that is coming out of our conveyor belts. The conveyor belts, basically, what we have done, instead of transporting clay around the London area, it works. So this is in Acton, close to where your studio is. And this is the Victoria Road crossover box, and this is the largest caterpillar structure in the world, and it used to be a square structure, but then we decided to change it, so we've got less concrete to use in general. And we've got the tunnels, we're going from here, it goes towards Euston, and from here down it was going towards West Ruislip. And as you can see here, these bits there are conveyor belts that basically take the clay all the way next doors to Wilton Euroterminal, where we've got a rail head, and these are the trains that we put it on, and it goes off to restoration of mines. And the aspiration is, like I said, to take the clay from there and use it somewhere on the project. Now, in order to do that, we put together some milestones on ourselves. The first one was the most difficult one, believe it or not. It's just a desktop study, technical note, where we had to see what specification we can put in, test specification, that will be beneficial for everyone, not just for the project. Validation, monitoring, inspection requirements, and the most important thing, to identify which structures can take the London clay to the timeframes that we had from Innovate UK to deliver this project. The second one was the large-scale calcination of London clay from the tunneling operations. This is also completed. Third one is when we got the clay back, to characterize it, so that it meets the requirements of the standards, because we have to meet that. If we didn't, it would be a problem, but we do. And optimize our concrete mixes with the elements that we have identified to make sure that we can pour that. Milestone 4 is where we are now, and it finishes end of October, and this is where we now have the batching plant trials and the actual concrete pour on site. Durability testing has begun, mixed design optimization has been completed, and life cycle assessment is 95% done. And then milestone 5, which is our last month in November, is just to write that report, which at the moment is about 80 pages, and we haven't even completed the durability testing, but we'll sort it out. So we can, finally, this one will be open to everyone, so everyone will have access. And I forgot to mention, what we have done with REAL, with HS2, everything we have done is on the HS2 legacy portal. So you can go in, there are two papers in there with all the data that we had, because I didn't go into too much detail now, but if anyone wants to join to look into that, you can do. Now, this is milestone 1. Well, like I said, we were looking into what can we do, what tests we need, what tests do we need to prove that we have to do for the industry to move on and build upon it. And these are the concrete mixes that we started looking into. So we had the calcined clay 50% because we already used that. A 35% because people were saying, okay, 50 might be too much. And then we went into the LC3s, which are now in the standards with the new BS 8500, the new British standards updates. So just to make ourselves more difficult, we decided to go with the LC3, which has 50% clinker, 35% calcined London clay, and 15% limestone fines. So we combine everything that is talked about in the cement industry at the moment. And this is the, something is missing. But this is the most difficult part that I was talking about the candidate elements. Where can we use the clay? Because it's not just a program. We had requirements in the contract with Innovate UK that it has to be accessible. So when DFT, DESNES, and whoever wants to visit it, they could see it. So it cannot be something that will be covered, which helps. It helps because we were looking into the walkways. So all good. Now this is the clay as it comes out. This is 42% moisture content over there. We had 38 as well when we sent it out for calcining. We sent about 12 tons. So you can imagine 5 tons of that is water, just transporting it over to Denmark. But it is what it is. Yeah, clay. Yeah. So this is a bit on the facility, how they were doing it, the calcination, because 42% you cannot just, dry it in lumps and hope for the best. So the first picture on the top left-hand side is essentially whoever has played with Play-Doh, you put the clay in and you compress it from the top and it comes out as nodules, yeah? And those edges, they've got something that cuts it, and you've got those small nodules that go up in this conveyor belt over there. Then they all go in the preheating facility. They dry out, so their color changes slightly. You can see that down there, how they look like. And then in the end, we get them in the grinder and comes into this powder, you can see here on the bottom right-hand side. Just to give you schematics of how the facility looks like, this is where the pictures go from. So you've got the clay going in that tower, which is compressing it, exactly as Play-Doh. It comes out, goes into the drying facility, then it goes into those stages down there. I don't know if that can be shown there. So it goes all those stages for heating, which is the calcination process. It comes out with a different color than where it will be. And then it goes into this facility here, which is your normal cement grinder, but this is smaller, specific for the calcined clay, and comes out to this powder ready to be used in concrete. Of course, we have to define how fine the powder will be based on the British standards, so we can make sure that we comply on that front as well. Now, one question that we get a lot is how do you decide which temperature you need? One of them is the activation energy. So what we do is we basically take a reference cement Portland cement. This is 195% clinker and the 5% limestone and gypsum. And we compare it with the strength data. So this one has only the 7-day test results, but you can see we get that as 100%. And we start calcining clay in a small kiln in the lab, and we start testing to see when we get the optimum reactivity. And for us, in this instance, was 825 degrees. So we just went on with 825 degrees to optimize the reactivity of the clay. Now, this is the mineralogy of the clay. And this is very interesting because down here you can see the calcite and dolomite. Those are the calcite, the limestone minerals that I was talking about. So these lines here, we've got the Ex-Clay, calcite 800, 700. These are the lab calcination temperatures at the University of Leeds. And you can see if you've got a pick, it means you've got a mineral. Yeah. Now in normal calcination processes, the limestone is heated and it gives us CO2 and it becomes clinker, it becomes different. What we saw here on the calcined industrial scale, we still have the picks for this, which means that the facility that we used is not calcining the limestone in the clay, which means our CO2 emissions from calcination of the clay is even lower than what we would expect, even that minor change. This was very interesting because we've never seen this before, but apparently this facility is seeing it and it's got a trademark process, how they do it. We don't know how they do it, basically. And we went again with everything. We started looking into SP, stands for super plasticizer, which is what keeps the concrete fluid without using too much water. So we started looking into different admixtures from CEng because they are our partner for admixtures. We started developing specific admixtures for the calcite London clay, and we started seeing how much do we need to actually get what we want. And we had there in the lab about 1.3% for this issue, 35% replacement. We ended up using about 1.7. Now this is only 2 pages of hundreds of spreadsheets. This is the development for the super plasticizer. Yeah, so we were playing with small scale lab concrete mixes to see what can we do. That's why you'll see you've got /1, /3, /7. We went up to 9 different variations of that super plasticizer just to make it work and find which one works better for us. And we're not looking only about strength development, which is here, the compressive strength, but we're also looking into the retention. So how long will the concrete remain flowable? Yeah. Very difficult with calcite clays. Now where we are, we've completed this. This was end of July. So we already have the 28-day test results. We're assessing them now. They're not part of this presentation because they just came in. We're looking into them and we're presenting them on Innovate UK and HS2 on Monday. But we had extensive test regime and you can see how the concrete looks like when we produce it in the lab. As normal concrete, just slightly different color. We'll come into my last slide, which are the options for where we're going to use it in 2 weeks' time. So what we want to see is not just complete the structure and leave it there and say, there you go, we did it. We want to get data afterwards, even though they're outside of the scope of the Innovate UK contract. We want to see how it reacts. Strain gauges we've got in there. We already have them on site in the formwork, and we've got thermal monitoring as well for the structure. So what we are planning to do, this here is a cross-section of the tunnel. So the dark green color are the walkways. So we've got the segments all around. We've got the light green over there is the invert concrete, which is basically what comes out as a cap at the bottom of the concrete, and then we've got the walkways. Now we've got the large walkway on the right-hand side is the emergency walkway. So if something happens to the trains, people can walk on them, and they're all throughout the tunnels. And the left one is the maintenance walkway, so anything that needs to be maintained by anyone, they use that. So the plan is that we pour these in the Norfolk Tunnel East Tunnel. And we've got these bit here, which are more temporary works, but they will be in place for at least 10 years. And this is a combination of a slab with a wall. And we will, again, put strain gauges in there and see how the reinforcement performs in there and how the strains go into the concrete, so we can get a little bit of data in the long term, and we can put them in durability modeling and see if they can perform in high structural elements. Because these one walkways, essentially, they will only take the weight of people walking on them, so it's not catastrophic for the tunnel if something goes wrong. Now what we've got upcoming works, I covered a little bit about this. We've got the NTE, the normal tunnel list structure. We're going to pour concrete in there. Unless something goes completely wrong with program and we have something, hope for the best. That's what happens when you work in tight time frames. You have to complete by the end of October, so everything needs to align and we complete. Hopefully we will do that. And bear in mind, we're talking about a 45-minute concrete pour, so we're preparing for 12 months non-stop for 45 minutes. Start at 10 o'clock, be gone by 11. So we review the durability test data, and what is important, we have a concrete mix that we compare it to, which is the normal concrete mix that most of the tier 1 contractors and big civil engineering works use with 50% GGBS. So we don't compare it what we would normally see with only Portland cement mixes, because no one uses them anymore. But we compare them to what we would use if we start the project now. Mm-hmm. The LCA, that's the final report that will be publicly available, and the end date is 30th of November. So expect that December with Christmas and everything, probably January, we will have the report published. That's it. Thank you.